In this video, we're going to take a look at how to factor an integer, and then also how to begin factoring polynomials. So we'll go further into factoring polynomials in the next few sections, but for now, we'll just kind of take a look at a few special cases. So we want to be able to find the greatest common factor and least common multiple of integers. And then we also want to be able to find the greatest common factor of monomials. And then we're going to begin to look at how to factor polynomials by using the greatest common factor, by recognizing special products, and also we're going to take a look at how to factor by grouping. So let's see. So let's start with what a prime number is. So you may or may not remember what a prime number is, but we'll refresh your memory. A prime number is any integer that's greater than 1 whose only positive factors are itself and 1. So a prime number, the only factors it can have are itself and 1. So only two numbers can go into a prime number evenly or without a remainder, and that's itself and 1. So for example, 2 is a prime number because its only factors are 1 and 2. And don't forget what a factor is. So basically that just means 1 times 2 is 2. Those are the only two numbers those are the only two integers that you can multiply and get the number 2. And then 3 would be another example of a prime number, again because its only factors are 1 and 3. So the only two integers you can multiply together and get 3 are 1 and 3. There's an infinite number of prime numbers. We can't go through them all, so just a third example would be like 17. Its only factors are 1 and 17. So again, the only two integers you can multiply together are 1 and 17 to actually get the number 17. So those are examples of prime numbers, so we might as well look at an example of something that's not prime. So the integer 12 is an example of a number that's not prime. And the reason it's not prime is because there's several things that go into 12 evenly without a remainder. So for example, 1, 2, 3, 4, and 6, those all are factors of 12. 12 goes into itself one time, 6 goes into 12 twice, 4 goes into 12 three times, 3 goes into 12 4 times, 2 goes into 12 6 times, and 1 goes into 12 times. So there's lots of factors of 12, and in order to be prime, it should only have two factors, 1 and itself. So one of the things we're going to need to know how to do is find the prime factorization of a positive integer. So to do that, you write the given integer as a product of prime numbers. So for example, if we take the number 12 and we come up with its prime factorization, we need to write 12 as the product of prime numbers. So for example, 12 is 2 times 6, but 6 is not prime. 6 itself can be broken down into 2 times 3. So 2 and 3, those are prime numbers. So 12, it turns out, is just 2 times 2 times 3. Those are all prime numbers. So we would write that as 12 equals 2 squared times 3, and that would be its prime factorization because 2 and 3 are prime numbers. So basically you can write the number 12, or if you want, you can write it as 2 squared times 3, which would be its prime factorization. Okay, so let's practice with a slightly more complicated integer. So let's find the prime factorization of 936. So the whole idea is we want to write 936, we want to write that as a product of prime numbers. So using only prime numbers. Well, that's not something you would probably just know off the top of your head. So you can just start breaking it down as you see fit. So for example, 936, that's even. So you know 2 will go into it. So it turns out 2 times 468 is 936. but 468 is even, so you know a 2 will go into that. So 468 divided by 2 is 234. 234 is another even number, so you know that a 2 will go into that. And when you divide that by 2, you get 117. And 117, 2 won't go into it because it's not even, but 3 does. 3 goes into that 39 times. And 39 will factor. So 39 is 3 times 13. And 13 is prime. 3 is prime and 2 is prime. So this would be the prime factorization. But we do like to use exponents just to write it a little bit neater. So 2 times 2 times 2 would be 2 cubed. 3 times 3 is 3 squared. And then there's just a 13 tagging along for the ride. So 936 written as the product of prime numbers would be 2 cubed times 3 squared times 13. So we call this the prime factorization of 936. So 2 cubed times 3 squared times 13. So those are all prime numbers. All right. Well, let's move on and talk about the greatest common factor. So the greatest common factor, which we abbreviate GCF, greatest common factor, the keyword there is common. What the greatest common factor is, so our definition will be the greatest common factor of 2 or more monomials is the common factor that has the greatest degree and the greatest numerical coefficient. So it's got to be factors that they have in common, and then as far as the variables go, it's the variable they have in common with the greatest degree, and then it's also the greatest numerical coefficient. So we're going to start with just numbers to get the hang of it with just numbers, and then we'll do numbers and variables. So a quick example, the greatest common factor of 24 and 36 is going to be 12. And the way we can verify that, or let's say you didn't know it was 12 and you're trying to come up with it, you can just take the two numbers, 24 and 36. So I got 24, write it as a product of primes. So do its prime factorization. So 24 is 2 times 2 times 2 times 3, because that would be 8 times 3 is 24. Take the other number that we're trying to find the GCF of and write its prime factorization. So 36 could be written as 2 times 2 times 3 times 3. And then you're looking for common factors. So for example, I see that 24 has a 2 and 36 has a 2. 24 has another 2 and 36 has another 2. 24 has a 3 and 36 has a 3. So that's everything they have in common. So the greatest common factor would be all three of those multiplied together. So 2, 2, and 3 makes 12. So that's how we know the greatest common factor of 24 and 36 is 12. Another way to think of the greatest common factor is 12. What this is the biggest integer that divides into 24 and 36 evenly. So in other words, it's the biggest integer that you can divide into 24 and 36 without a remainder. So that's another way to think of the greatest common factor. So what I'm showing you here is a way you can come up with it if you don't know that off the top of your head. Because, sometimes the numbers will be numbers we don't work with very often. So we need a way to kind of come up with it if we don't just know it. All right, so let's give it a try. So let's find the greatest common factor of 48 u squared v squared and 60 u times v cubed times w. So what we want to do is write this as the product of primes. So let's start with 48u squared v squared. So 48 would be 2 times 24, and then u squared would be u times u, and v squared would be v times v. And then 24 would be 4 times 6, and then u times u, v times v. And then 4 would be 2 times 2, and 6 would be 2 times 3. And then we can't break it down any farther because everything's prime. Well, now let's go do 60 u v cubed w. So if you have 60 u v cubed w, 60 would be, you could break it down however you want. It would be 4 times 15. And then we have 1 u, but we have 3 v's and a w. And then 4 is 2 times 2. 15 is 3 times 5. And then we have u, v, 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 and then a w. And a w. And then we want to go find everything they have in common. Everything they have in common. So if we go back and look, we've got a 2 that they share. There's another 2 that they share. There's a 3 that they share. There's a u that they share. There's a v that they have in common. There's another v that they have in common. But this u doesn't have a u, then they don't have a w. There's no 5s. So our greatest common factor will be, write down everything they have in common. So it'll be 2 times 2 times 3 times u times v times v. And if we multiply that out, that's 12uv squared. So that would be the greatest common factor of those two things. So when we learn how to divide with variables, you'll see that this still works. This is still the biggest monomial that'll divide into both of those monomials without a remainder. But for now, we have an easy way to find it. Just write out the prime factorization of both numbers, and then for the greatest common factor, just write down everything they have in common and multiply it out. So let's try that one more time. So let's do the greatest common factor of 8ax squared, 12a squared x. So let's do 8ax squared first. So 8 would be 2 times 2 times 2, and then an a and 2 x's. And then 12a squared x would be 2 times 2 times 3 to get 12. There's 2 a's and 1 x. So in common, they have this 2 and this 2. They have another 2. They don't have a 3 in common, but they do have an a. And they both have 1 x that's in common. So the greatest common factor will be 2 times 2 times a times x. So it'll be 4ax. All right. So the other thing we were going to talk about was the least common multiple. So let's take a look at that. So the least common multiple is exactly pretty much what it says it is. We call it the LCM for short, and it's the smallest, least, common positive multiple. So let's take a look at one. So let's find the least common multiple of 48 and 60. So the way we can come up with this is we can do the prime factorization again. So 48 would be 2 times 24, which would be 2 times 4 times 6, which would be 2. That'll break up into two 2's, and that'll be a 2 and a 3. And then let's do 60. 60 would be 4 and 15, which is 2 and 2, 3 and a 5. Okay, so now we don't necessarily want what they have in common. So this is 2 to the 4th times 3, and this is 2 squared times 3 times 5. So the least common multiple, we don't necessarily want what they have in common. What we want to do is, in 48, we see that we have a 2 to the 4th. In 60, we have a 2 squared. Well, 2 to the 4th, there's more 2's here than there are here. So we're going to grab the one that has the most. So 2 to the 4th, that's got the most 2's in it. So we're going to grab that one. And they both have a 3 to the 1st. So the biggest exponent on 3 is 1. So we're just going to grab that 3. And then this one doesn't have any 5's, but this one does have a 5. So that's the biggest exponent on the 5. So basically what you're going to go do is you're going to go look at the prime factorizations of the numbers, and you're going to grab the one that has the biggest exponent. You got to make sure you grab one for each factor. So I needed to grab some 2's, some 3's, and some 5's. And I grabbed 2 to the 4th because it's got the biggest exponent, 3 to the 1st because it's got the biggest exponent, and 5 to the 1st because it's got the biggest exponent. And then you just multiply those together, and you get 240. And another way to think of what this is the smallest number that 48 and 60 both divide into without a remainder. So, 60 will divide into 120 without a remainder, but 48 will not go into 120 without a remainder. 60 will go into 180 without a remainder, but 48 will not go into it. So 240 is the first number you come to that 60 will divide into without a remainder and 48 will divide into without a remainder. So we call that the least common multiple. All right, so with that stuff in mind, we can now start to look at how to factor polynomials. And again, we're just going to begin this process with this section. We're not going to, we're going to keep talking about factoring polynomials as the chapter goes on. So for now, to factor a polynomial, you rewrite it as a product of other polynomials. So when we ask you to factor a polynomial, we're asking you to write it as the product of several other polynomials. So the first few ways we're going to look at doing this, we're going to start by, the very first thing you should always do is look and see if the polynomials have a greatest common factor. If they do, we're going to factor that out. Now, if the greatest common factor is just 1, that's the only thing they have in common is a positive 1, then we're not going to bother factoring out a positive 1 because it doesn't really change the appearance of the polynomial. Well, after we do that, we're going to check and see if the polynomial is a perfect square trinomial, if it's the difference of squares, the sum of cubes, or difference of cubes. If it is one of those things, we're going to factor it as is appropriate for which one it is. And that's what we're going to talk about next, is what exactly is a perfect square trinomial, what's the difference of squares, what's the sum of cubes, or difference of cubes. So let's take a look at those real quick. So we're going to call these special products. So these come up a lot. That's why they're special. They show up enough that they kind of get their own name. So basically, if you have, this is called a binomial. We talked about that earlier in the chapter. So if you have a binomial and you square it, it'll always work out with this pattern. So a plus b, when you square that, it turns out that it'll always multiply out and be a squared plus double whatever a times b is plus b squared. So every single time you square a binomial with a plus sign, a plus b, it'll end up the front number squared plus double the front number times the back number plus the back number squared. Well, if it's a minus b squared, so the only difference is a minus, then the only thing that'll change over here is it'll be a squared minus double ab plus b squared. So we call those perfect square trinomials. Now, we're going to talk about factoring them though. So what we want to do is we want to recognize this so that we can factor it like this, because we want to write it as the product of two things. So we'll do some examples here in a sec. Well, sometimes we run into what's called the difference of squares. So it turns out if you take a plus b and you multiply it by a minus b, where the front numbers are the same, the back numbers are the same, but the only difference is it's a plus and a minus. Every time you multiply those together, it always ends up being the front number squared minus the back number squared. So we call that the difference, because it's minus, of squares, because they're both being squared. And what we're going to do with it is we want to recognize this so we can factor it like that. And again, we'll see an example of that here in a sec. And then we got two more. It turns out if you see the sum of two things being cubed, you can factor it in this pattern here. See if I can make it a little easier to see. So if you have the sum of two things cubed, it'll always factor into the front number plus the back number times the quantity the front number squared minus the front number times the back number plus the back number squared. And then if it's instead of plus, if it's minus, it's going to be a similar pattern, except for this will be a negative sign, and then these will both be plus. Now notice there is a sum of cubes and a difference of cubes, but for if you have two things being squared, it has to be minus. It has to be the difference of squares. There is no special factoring for a squared plus b squared. All right, so we're going to use those. So let's take a look. So this definitely takes some practice. So we're going to factor 10ab cubed minus 15a squared b squared. So the first thing we want to do is come up with the greatest common factor. So we need the biggest number that'll divide into 10 and 15 evenly. So the biggest number that goes into both of those evenly is 5. And then they both have one a in common, and they both have two b's in common. So if you look, this one has 3 b's, this one has 2. So they both have 2 in common. And they both have at least one a. This one has one a, this has 2. So they both have an a. And the biggest number that goes into 10 and 15 evenly is 5. So the greatest common factor is 5ab squared. Now you can still figure out the greatest common factor by doing what we showed you earlier, by writing out all the primes and then writing down everything they have in common and multiplying it together. So we want to factor 5ab squared out. So to factor out means we write the greatest common factor and then parentheses, and then we think, well, what if I take 5ab squared away from these two terms, what would be left? So you just got to ask yourself, 5 times what would be 10? Well, 5 times 2 would be 10. And then a times what would be a? And it'd be a times 1. And then b squared times what would be b cubed? And it'd be b. And then 5 times what would be negative 15? It'd be negative 3. And then a times what would be a squared? And it would be a. And then b squared times what would be b squared? And it would be 1. And then we just clean that up, make it look a little better. So we just have 2 times 1 times b would be 2b 3 times a times 1 would be negative 3a. So this polynomial factors into 5ab squared times 2b minus 3a. So we took this polynomial and we wrote it as the product of 5ab squared times 2b minus 3a. And then you can actually check these, even though it's not an equation, you're not solving an equation, you can still check your answer. So to check and make sure you did that correctly, all you gotta do is take your answer and then distribute and make sure you get what you started with. So 5 times 2 is 10, a times 1 is a, b squared times b is b cubed, 5 times negative 3 is negative 15, a times a is a squared, b squared times 1 is b squared. And that's exactly what we started with. So just multiply it back in and make sure you get what you started with. All right, let's look at another one. So let's factor z squared plus 6z plus 9. Let's see how we can maybe factor that one. Let's start with coming up with the greatest common factor. So z squared, well, there's just a 1 sitting out front. So 1, 6, and 9, the only thing that they have in common is a 1. And then this has 2 z's, this has 1 z, but this doesn't have any z's. So there are no z's that it has in common. So the greatest common factor is just 1. There's nothing else that they have in common. So greatest common factor is 1. And when the greatest common factor is 1, there's no need to factor it out. Like you can write 1, but 1 times itself. So when you factor out a 1, you're just going to end up with the same thing you had to start with. Because 1 times z squared is z squared, 1 times 6z is 6z, 1 times 9 is 9. So there's no reason to factor out the greatest common factor if it's just a positive 1. So instead, we're going to move on and see if maybe it's one of our special products. So let's see if maybe this will be a perfect square trinomial, or the difference of squares, or sum or difference of cubes. Well, the difference of squares only had 2 terms. So if we go back and look at that, the difference of squares only had 2 terms, something squared minus something squared. Well, we have 3 terms, so it's not going to be that. The sum or difference of cubes has 2 things being added or 2 things being subtracted that are both being cubed, and we have 3 things, so it can't be that. So it's gonna, if it's going to be anything, it's got to be a perfect square trinomial. So let's see if we can recognize it as a perfect square trinomial. So z squared we could write as z squared. 6z we could write as 2 times 1 times z. Well, to get 6, we'd have, let's try that again, be 2 times 3 times z to get the 6. So 2 times 3 times z. And then 9 we could write as 3 squared. Now, how did I know to write it that way? Well, I didn't necessarily know. I was just hoping that it would be a perfect square trinomial. And if you go back and look, the perfect square trinomial has got to be something squared plus 2 times 2 other things plus something squared again. So that was kind of my motivation for writing this as z squared, and then 2 times 3 times z, and then 3 squared. So our perfect square, that way I don't have to scroll back up. Our perfect square trinomial was a squared plus 2ab plus b squared will always factor into a plus b squared. Well, if you look, this is like our a, and then this is like our b. So if you look, we have exactly this pattern. I have a squared plus 2ab plus b squared. It's exactly this pattern. So that tells me that this equals this, which equals, I can now factor it as a plus b times itself, which when we simplify, since it's anything times itself, it's just that squared. So we're trying to match this pattern. So something squared plus 2 times that number times something else plus that other number squared. So we can check. Let's check our answer. So z plus 3 squared would be z plus 3, z plus 3. So z, we'll multiply these together, it'd be z times z plus z times 3 plus 3 times z plus 3 times 3. And we'll get z squared plus 6z plus 9, which is exactly what we started with. It's exactly what we started with. So that would be the correct way to factor. So we took this polynomial and wrote it as the product of two other polynomials, in this case z plus 3 squared. Let's try another one. So again, I've got three terms. I got 4x squared minus 4xy plus y squared. So I've got three terms. So it's not the difference of squares, and it's not the sum or difference of cubes. So we can rule those out. Let's come up with the greatest common factor. So I've got a 4, and a 1. Well, the only thing those are going to have in common is a 1. This has two x's, this has one x, this doesn't have any x's. This doesn't have any y's, but those two do. So the only thing they have in common is a positive 1. So again, there's no need to factor out the greatest common factor. So maybe we can make it look like a perfect square trinomial. So I do have a negative. So again, so I don't have to scroll back up. So our perfect square trinomial, one of them was a squared minus 2ab plus b squared. We'll always factor into a minus b squared. So let's see if we can't make this one look like this. So I need it to be something squared. Well, 4x squared would be 2x squared. And I need it to be minus 2 times something else. So it would be minus 2. Well, it has to be 4. So 2. And then let's see, times y. And then y squared. So plus y squared. So let's see if that'll work. So a. This would be our a. Maybe. So there's our A, there's B, and there's B. So we have A squared minus 2AB plus B squared. So that tells me that this equaled that, which equals, and now I can use my little factoring thing here. So I know that this is going to be A minus B times itself. Let's try that again. So our a is 2x, so it'd be 2x, and then our b is y, so it'd be minus y, and then times itself, which we more conveniently write as 2x minus y squared. So again, we can check that. So to check that our answer is correct, our factoring is correct, we'll have 2x minus y squared, which is 2x minus y, 2x minus y. That'll be 2x times 2x, and then 2x times negative y, and then negative y times 2x, and a negative y times negative y. Multiply those together, you get 4x squared, and then we'll have negative 4xy, and then we'll have plus y squared, which is exactly what we started with. So, the tricky part is practicing how to rewrite these things so that it matches, one of our little special products, in this case, the perfect square trinomial. All right, so let's try another one. So we have 25x squared minus 16y squared. So let's find its greatest common factor. So 25 breaks that down into a 5 times 5, and that breaks down into 2 to the 4th. So they don't have anything in common other than a 1. This has x's and this has y's. So again, the greatest common factor is just 1. But I do have two terms, and I do see some squares, and they're being subtracted. So that makes me think of the difference of squares, which was a squared minus b squared, which always factors into a plus b, a minus b. So let's see if we can't make that work. So I need something squared. Well, I could rewrite 25 as 5 squared. So we could do, instead of 25x squared, we could write it as 5x squared. And then I'll have something squared like we need. And then instead of 16y squared, I can write that as 4y squared. And then a, this will be b. So we have a squared minus b squared. So now we know exactly how it factors. It factors into these two things. So this will be a, so it'll be a plus b times a minus b. And then that'll be our factored form. So this is the polynomial, and this is what the polynomial looks like when it's factored. So keep in mind, this is equivalent to this, which is equivalent to this. So these are always the exact same polynomial. This one's just factored. Let's try another one. So let's factor this one. Let's do the greatest common factor first. So the only thing that goes into 3 is 3 in itself, or 3 and 1. But 3 also does go into 48, so they both have a 3 in common. This one has 5 x's and this one has 1 x, so they do have an x in common. So this time we actually do have a greatest common factor that's worth factoring out. So we'll factor out the greatest common factor. So now we got to ask ourselves, 3 times what is 3? And it's 1. X times what is x to the 5th? It'd be x to the 4th. 3 times what is negative 48? It'd be negative 16. And then x times what is x? And it would be 1. And then we clean that up. It'll be x to the 4th minus 16. But we want to be careful because we factored out the greatest common factor, but it turns out x to the 4th minus 16 is the difference of squares. So we always want to be on the lookout for one of our special products. So the difference of squares was a squared minus b squared, which always factors into a plus b, a minus b. So for us, let's see if we can't make that. So x to the 4th would be x squared squared, and then 16 is 4 squared. So this would be our x, our little formula, and that would be b. So we could write this as 3x times a plus b, and then a minus b. But once again, after doing that, we see that we have x squared minus 4. And x squared minus 4 could be written as x squared minus 2 squared, which is the difference of cubes once again. So it'll factor even some more. So we'll have 3x, and then we'll have, this should have been plus back here, sorry. We'll have x squared plus 4. That one doesn't factor anymore because we don't have a sum of squares. So the fact that that's plus means we can't factor that one anymore. But this one, we have a squared minus b squared. So it'll end up being a plus b, a minus b. So we end up with those 4 factors. So 3x is a factor, x squared plus 4 is a factor, x plus 2 is a factor, and x minus 2 is a factor. So it started out as 3x to the 5th minus 48x, but when you write it in factored form, after you factor it, you end up with those 4. So we had to use the difference of squares once, and then we had to do it again twice. And then we also factored out the GCF. Let's try another one. All right, so in this case, we have y cubed minus 1. So hopefully you can just kind of look at it and tell that the only thing that y cubed and 1 have in common is 1, because there is a 1 sitting out. So if you factor out the 1, it doesn't really do anything to it. You can take the 1 out, but it doesn't really change your polynomial. So it's not really worth our time. So maybe it'll be one of our special products. We do have something cubed, so that's kind of a big hint as to which special product we would want to take a look at. So we have a subtraction sign, so we have, this could be the difference of cubes, which was a cubed minus b cubed, always factors into a minus b, a squared plus ab plus b squared. So let's see if we can't make our polynomial look like that. So this will equal y cubed minus 1 cubed. And then this will be our a. This will be our b for our little formula. And then we'll just use our little difference of cubes here. And we'll have a minus b times a squared plus ab plus b squared. And then if we clean that up, we end up with y squared plus y plus 1. And then y squared plus y plus 1, no matter how hard you try, you will not be able to write it as a perfect square trinomial. So this is not a perfect square trinomial. So just because you look at a polynomial and you have 3 terms doesn't necessarily mean it's going to be a perfect square trinomial. So no matter how hard you try to rewrite that thing, you're not going to get it to rewrite as a squared plus 2ab plus b squared. It's just not going to happen. And again, you can check this by multiplying that binomial times that trinomial and see if you get back to the original polynomial that they gave us to factor. All right, we got 2 other ones we want to take a look at. So let's do 3xy minus 4 minus 6x minus 2y. So let's try to find the greatest common factor. Well, 3, 4, 6, and 2, the only thing they have in common is a 1. And this has x's, but this one doesn't. And this one has y's, and this one doesn't. So they don't have any variables in common either. So there is no greatest common factor other than 1, which we don't really bother with. and it's got 4 terms. So 1, 2, 3, 4. So it's definitely not a perfect square trinomial, and it's not the difference of squares, and it's not the sum or difference of cubes. So this doesn't really, as it sits, look like any of our special products. So in this case, we're going to try to do something called factor by grouping. So if you look, um, I've got 2 terms that have an x in them. So 3xy and this negative 6x both have an x. And then the other ones, the negative 4 and the 2y, they both have a 2 in common. So these 2 terms right here, we're going to group those together. So I'm going to put these 2 together, and then I'm going to put these 2 together. And if you look, 3xy minus 6x, they both have an x in common. So I'm going to take that out. So if I take that away from them, 3 times 1 is 3, x times 1 is x, and then there's a y that I didn't take out. And then 3 times negative 2 is negative 6, and then x times 1 is x. And then these other 2 terms that I grouped together, notice how they both have a 2 in common. So I'm going to take that 2 out. And then 2 times negative 2 is negative 4. And then 2 times y is 2y. Well, now if I clean that up a little bit, I just have y minus 2. In this other one, I have y minus 2. So the reason that helps us is if you take a look, this term right here, and this term right here, they both have a y minus 2. So they have a common factor. So this equaled that, which equaled that, which equals this. And they both have a y minus 2. So I'm going to factor out the y minus 2, and that'll leave me a 3x plus 2. So if I take this y minus 2 and this y minus 2 out, it's right there. And then what it leaves me, it leaves 3x plus 2 right there. And then this would be the factored form of that original polynomial. And once again, you can multiply these two things together and you should get what we started with, and that's how you can check your answer. So the only reason that this actually worked out is because after I grouped 2 of them together and I factored out a 3x and a 2, it left me with the exact same factor, y minus 2, y minus 2. That doesn't always happen. So if that doesn't happen, then this particular way of factoring, it won't do you any good. All right, let's look at one more. So let's factor, once again, we have 4 different terms here, so it's not going to be any of our special products when you look at it. And the greatest common factor, 1, 4, 4, and 4, the only thing they have in common is a 1. Some of them have t's, some of them have w's, some of them have nothing, so there's no variables in common. So the greatest common factor is just 1, so we're not going to bother factoring it out. But if you look, I do have 2 terms that both have a t in common, so I'm going to group those together. And then the other 2 terms both have a 4 in common. And then if I take away the t that they have in common, it'll leave me t minus 4. And if I take the 4 that they have in common, I end up with negative w squared plus 1. Well, and when I did that, t minus 4 and negative w squared plus 1, unlike what happened in the last example, these are not the same thing. So I can't factor that out because they're not common. They don't both have the same thing in common. So this is just a big dead end. Grouping them together this way got me nowhere. And negative w squared plus 1, um, even if we factor it, it's got w's and this has t's. So I'm never going to have anything that I can factor out of the whole polynomial. So that was a big dead end. So let's see if we can't group them together in a different manner. So what if instead of putting the ones with t together and the ones with 4 together, what if we do t squared minus 4t plus 4? What if we put those three together? Because those might be a perfect square trinomial. So I could write that as t squared minus 2 times t plus 2 squared minus 4w squared. And sure enough, we have a squared minus 2ab plus b squared. So it is. It's one of our perfect square trinomials. So we end up with t minus 2 squared minus 4w squared. And then as soon as we do that, we see that a squared minus, we might even be able to do a difference of squares here. So let's see. This will be t minus 2 squared minus, and then 4w squared would be 2w squared. And then sure enough, this is a, this is b. So we know this factors into a plus b times a minus b, which we don't need all the brackets, I suppose. We could write it as t minus 2 plus 2w, and then t minus 2 minus 2w. So that would be how we would factor that original polynomial. So this particular situation, this last example, it's pretty rare that a polynomial would allow you to group it together, get a perfect square trinomial, and then after that get the difference of two squares. So that's pretty rare. The example is more just, to get more practice with perfect square trinomials and the difference of squares and being able to recognize them, because that's the hardest part. The little formulas to factor them is not that difficult. It's just recognizing them.